Morning everybody, and welcome to the KARALIT CFD 2.1 demo. The demo I'm going to show you today is related to an internal flow analysis. So let's start from the demo project, creating a new project, and let's choose the internal flow app among the 6 that KARALIT CFD offers you. Once you have chosen the app, you need to specify which is the geometry we are going to use. So in this case is an intake of an engine of a Formula SAE car. As you can see, the STL is not customized at all, so it's the one just coming straight from the CAD. So we need to select which boundaries are going to be used as inlet or outlet or whatever. In order to do that, we will use a very usable and very good facilities of KARALIT CFD, which is the surface selection. So the surface selection is working like that. You add the boundary you like, let's call it inlet, and through one of the possibility that you have to select the triangles on the STL, you use the normal selection, and with a simple click we are going to create the inlet. We are going to do the same for the other 4 surfaces, so let's add 4 more boundaries. So 1, 2, 3, 4. So this one is going to be the outlet 4, and it's going to be the same here. The 3 is going to be the outlet 3, and we're going to select like that. The 2, outlet 2, is going to be that, and the last one, outlet 1. That's it. We have specified the surface that we're going to need for the boundary condition and for the monitoring purposes of our demo. Let's go to the second step, which is the LGR. LGR means local grid refinement. Is our meshing, Cartesian meshing tool. Is an anisotropic Cartesian mesh refined on the wall. So we are going to start from an initial grid spacing that we specify here. And you see that there is a mesh everywhere because we didn't yet tell the mesher, the grid generator, where it's going to be propagated. We'll do it a little bit later. Let's go to the selection, to the resolution on the different surfaces. We can specify different resolution. For this demo we are going just to specify this kind of resolution. So 2 millimeters and tangential 0.01. The normal layer and tangential layer in this specific demo, they are going to not to be used because you see they are the same size of the initial spacing. Those layers are usually used when the geometry is big enough for outflow kind of analysis, external analysis, in order to propagate the mesh resolution near the surface in a better way toward the external resolution. Okay, so in this case we basically not going to use it, so let's use the same resolutions as the initial grid spacing for all our normal layer, tangential layer. We are going to specify so a 2 millimeter resolution normal to the wall on each surfaces of the STL, including the inlet and outlet. A tangential of 0.01, which means that the cells is going to be stretched along the tangential direction. Now, in order to be able to tell the mesh where it's going to be propagated, we use the fluid point facilities. I added the fluid points, and you see that it's automatically created inside the geometry. I can also move it with the mouse. So it's basically, this is going to tell us that the mesh is going to be propagated inside the CAD. So basically it's done. I just start local grid refinement, and in a couple of seconds I'm going to have the Cartesian mesh generated in this complex 3D geometry. So you know there are all the processes done here in the background, the refinement and the surfaces. There is the selection of the cells and the boundary cells, and basically the meshing process is done. So I can see here, you know, the resolution near to the wall. I can of course improve it, I can do a finer mesh at the wall, I can do whatever I like. So this is basically what's happened. Now I'm done with the mesh. I'm closing the mesh process and go to the fluid. So let's simulate a turbulent viscous simulation with gas. Let's use the density here. In terms of initialization, I can specify those values: 10 meters per second, minus 10 meters per second, because it's a piping in different direction. I'm gonna need to use the Spallard-Almaraz turbulence model. I could choose among k omega and kg. I'm going to monitor the x momentum during the run, and I'm going to define a convergence criteria to stop at -4, for example. That's it. In this case, I don't need other setting, neither pressure gradient term or rotating flows, because we don't have any specific needs in this specific case. Boundary conditions. So the intake is the overall surfaces, so it's going to be a non-slip adiabatic wall, for example. We can do different kind of characterization of the wall, of the surfaces, even a thermal characterization, porosity, and things like that. The inlet is going to be a mass flow rate inlet, which is a mass flow rate of 0.07 kilograms per second. And I'm going to monitor both pressure and mass flow rate. Even if mass flow rate is imposed, we can just use it during the monitor to check. In the outlet, I'm going to use a pressure outlet of a little bit less than the atmospheric one, which is typical of engine components. So pressure outlet of intakes like that. So 81, the same outlet pressure here. Even here I'm going to monitor mass flow rate, so we can control the balance of the mass flow rate during the run. I think I forgot to activate the monitor on the first two outlets. That's it. Then the last tab is the simulation. So I'm going to use an implicit scheme with a symmetric TVD. In this case I can use upwind, first order, whatever. I can split my domain in 2 cores, 3 cores, 4 cores, depending on many cores, how big is your model. You can leverage of the possibility that we give you to leverage of the hardware infrastructure that you have by using as many cores as you wish. And basically our setup is done. There is a warning because I didn't set the wall as adiabatic wall. Non-slip adiabatic wall being a turbulence calculation. So basically I'm done, I click start and I'm off. I'm finished with the setup in a couple of minutes, and the code is going to perform the immersion process now. So it's going to detect which are the fluid cells, the solid cells, and the boundary cells in a proper way, doing everything in the background. You don't need to do anything, and in a couple of minutes the solver is starting. And we are going to just wait 50 iterations in order to have a first look of the initial results. Of course, the run will need more run time in order to have a proper balance, a proper convergence. But just to give you an overall idea that in a couple of minutes you set up a CFD analysis of a complex 3D geometries thanks to the immersed boundary technology that we offer you. So you see that there are already the first iteration. During the monitor you are going to monitor the x momentum as basic criteria, convergence criteria, but we also impose the mass flow rate. So there is 0.06 is going to be 0.07 at region, and the other 4 outlets are going to balance the same, of course, same levels in order to balance the mass flow rate between inlet and outlet. And the pressure as well is going to be monitored during the run. All these things can be, saved as pictures during at the end, or if you want to save the convergence criteria and different things. The log is still here. During the run, keeping in consideration that during the run you are going to be able to open a new project and do a different configuration of the fluid properties or things like that, or do, for example, a modification of your initial design and do a parametric variation. The code can very easily be run also in batch through a common script scheme that you can run and propagate it on a cluster or anything like that. So it's pretty convenient and pretty easy to to be performed. We are almost done with 50 iterations, and we are going to use also the facility that is available in the code. You see that we can move and change the section in our previews. You have also here, you see contours, streamlines, vector isosurface, which is the integrated post-processors. In this case, we are going, for example, after 50 iterations, to monitor to visualize the velocity contours, okay, in our domain. Of course, you can also move your section in a different way, so you can control the solutions as you wish. Of course, there is a legend as well, which is going to give you, the section range or the domain range, depending on how you are going to visualize your results, etc., etc. So this, of course, is very useful to have a first qualitative and quantitative analysis of your solution. Of course, you still have the possibility to visualize with external post-processor like TechPlot and Cited ParaView that you are going to choose here in the Preferences options menu. Output, if you have all three post-processors, you select 3, in order that during the saving, KARALIT will save the solution for the 3 post-processors. Otherwise, you select just the one that you have available, and so you can visualize in a more detailed way with a real post-processor or with a complete post-processor the analysis. So that's basically concluding my demo of today. I thank you for your attention, and for any additional details or clarification or information you might need, please contact us at sales@karalit.com, and we'll be very happy to reply to you and give you any additional information. Thank you very much. Bye-bye.